Welcome everyone. We're continuing our series on momentum. We're in the third lesson. We've done a lot already. We're starting to get to the nitty-gritty, which is really nice, and it's lots and very exciting. So, this is the prevailing thought for this lesson. What do people mean when they say something has gained or lost momentum? Because we hear that often. They'll go, the golf ball gained momentum as it rolled down the hill. Or the cyclist was going up a hill and they lost momentum, which is why it's really difficult to cycle uphill. Or sometimes we even do it in terms of work or in terms of they gained momentum in getting something done. So we speak about it, but what does it mean in terms of science? What's the nitty-gritty behind that, okay? So that's what we're going to look at today. By now, you should know the definition, the equation, the properties, and how Newton's laws affects it. So today, we're going to look at, we'll go back there quickly, change in momentum. That's what we're focusing on. There are some key words that we need to get. Number one, initial momentum. What do we mean by initial? What does initial mean? Okay, we know what momentum means. We're going to look at final momentum. What does the word final mean? Where does it come into play? Okay? And then change in momentum. How the object's momentum changes is actually really important for us. Okay? Let's break change in momentum down. So change in momentum, first of all, is a vector. Momentum is a vector. So change in momentum is a vector, because when we change momentum, it's not a new concept, it's not a new quantity, we're just looking at how it differs, whether it gets bigger or smaller, did we change direction, all of those sort of things, because how momentum changes affects the motion of our object, okay? Because it's a vector, before we get there, sorry, for momentum to change, velocity changes. We have spoken about in the past, when we did Newton's second law, that it's possible for the mass to change. Absolutely. But we're not going to consider that in our study of momentum, okay? So we're going to consider what happens when the velocity changes, okay? When velocity changes, it's a vector that's changing. Because it's a vector, it has a direction. That direction is the same as the net force. This is what we have to keep in our minds. Momentum is a vector. The direction of momentum is the same as the velocity. When the velocity changes, there's acceleration. The direction of the acceleration is the same as the net force. That net force causes the change in momentum. That change in momentum has the same direction as the net force. It's all about the net force here. So change in momentum is related to acceleration. We've got to think about this one carefully when we look at the direction of the change in momentum, because an object might not change its physical direction. So in other words, I could have something going forward, but the change in momentum is backwards, and that happens when it slows down, okay? We're also going to consider what happens when an object changes direction completely. Then where's the change in momentum? And here, using our negatives, when we look at it, because we're dealing with vectors, becomes very important. So we've got to keep our head on straight when it comes to direction, okay? So, we have thought about this. We've done this. What happens when a net force is applied to an object? There's several things. You've done net force on objects lots over the years, okay? You would have done it in lots of places other than in your senior years as physical science. So a net force can do lots of things. It can change the velocity, it can change the acceleration, it can start and stop objects moving. But essentially, the big thing for us is when a net force acts on an object, the object's going to change its velocity. So that's important, but let me just remind you again, okay? So, a force can do this. It can start an object moving. So if it had zero velocity and it starts moving, its momentum is going to have changed because the net force is causing the velocity to change. It can start and make an object speed up, so it's already moving, it gets faster, slow down, like driving in a car and putting the brakes on, or it can make an object stop. All of those things involve a change in velocity from a net force, okay? It can cause an object to change direction. We all know that, like when we turn a corner. We're not going to consider a change in direction at 90 degrees when it comes to momentum, but a change in direction definitely changes momentum. And we're really going to talk about change in direction when something hits a wall and bounces back or hits a floor and bounces up. We're not going to do anything that's two-dimensional, so it goes off at angles. Okay, we're not doing that. We're going to make it simple. An object can change its shape. Now, if we change its shape, it doesn't change its momentum. Okay, it's like playing with Play-Doh when you were little, and you squish it and squash it and all those sort of things, okay? That doesn't affect momentum. We can also cause it to rotate, spin, go in circles. That has nothing to do with the momentum we're working with, okay? You do get rotational momentum, but we don't do that at school. Study physics when you get to varsity, hopefully some of you will, and you'll do it there, okay? So here, that's not something that's within our scheme of what we're doing. So the three that is important are those ones, okay? Let's go back here, is the fact that all three of these things involve the vector changing, okay? So a change in direction changes the vector. And in fact, when you change the direction of motion, you actually have technically caused acceleration to happen because you've changed the direction of a vector. That means the vector's changed. Makes sense? And all the first two involve a change in velocity, which must change the momentum. They go together. All right, so change in momentum is a vector. And this is the one where it starts to get a little hazy, okay? It has to have direction. How do we determine the direction? We're going to go back to Newton's second law in terms of momentum. F net is change in momentum over change in time. Now, time is a scalar. Time has no direction, so it's not important, okay? That means we have to consider this vector and that vector. Because F net has, and we've got that equal sign, these directions have to be the same. So the direction of my F net will be the direction of my change in momentum. So if F net is to the right, change in momentum is to the right, regardless of the direction that the object's moving in. And this all sounds quite weird at the moment. Don't worry, we're going to break it down a little bit further later on. If change in momentum is upwards, then the net force must have been upwards. If the net force is backwards, then the change in momentum is backwards. So whatever direction the net force is in, the change in momentum is the same, okay? They go together. Net force, the direction of net force is the same as the direction of the acceleration as well. We spent a lot of time on that last time, okay? So, I need you, because we're going to go for a short break, just to try and get your head around F net direction equal to change in momentum direction. okay? And then we'll work through it in the next section. So I'll see you in a couple of minutes.